Hey there. Today we are going to talk about mold. So you have probably never heard of this before, and that is expected. This is the first time we are talking about this topic, but it's not the last. We are going to talk about moles throughout the year in chemistry. So this is a great basic skill to master now to avoid confusion later. So first up, what does a mole mean? It has nothing to do with the animal called a mole, and it has nothing to do with a weird thing on your skin. A mole in chemistry is a certain amount of a substance. So the key thing to know here right off the bat is that a mole is an amount. It's an amount of substance that contains the same number of atoms as 12 grams of carbon-12. Now, this is not going to be the most important thing to remember, that a mole is the same amount of atoms as 12 grams of carbon-12, but we like you to know that it's not totally random where this number comes from. A lot of chemistry calculations are going to be carried out with this unit called moles instead of grams. And again, moles is an amount. So I like us to first think, what are some other words that mean an amount, that mean a number? So think through that for a second. What are some words that mean a number? So here's a few possibilities. We've got a dozen, and usually we all know that a dozen specifically means 12. So a word, dozen, means a number, 12. Trio is a word, but it means a number, 3. Duet and pair both are words, but they mean a number, 2. Octet we've talked about a little bit in chemistry. That means 8 things. So what we see here is that a word can mean a numerical value, and that's what a mole is. So a mole is a counting unit, just like a dozen. It is a number. So here's the ultimate question. Miss Hammer, you keep saying a mole means a number. What number? So how many atoms is it? Well, it's Avogadro's number. It's such an important number, we give it a name, Avogadro's number. He's the scientist that figured this out. It's the number of particles in a mole, and that magical number, here we go, is 6.02 times 10 to the 23rd. 6.02 times 10 to the 23rd. That is 1 mole of somethings. This could be a mole of people. If you had a mole of people, it would be 6.02 times 10 to the 23rd people. That's more people than our existence on Earth today, by the way. So a mole is a big, gigantic number. This number is 602 with 21 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Woo! That is a big number. So a mole of atoms is a lot of atoms. So why do we care? What's the big idea here? This is a big important concept. If you have 1 mole of an element, you have 6.02 times 10 to the 23rd atoms. I'm going to say that again. If you have 1 mole of an element, you have 6.02 times 10 to the 23rd atoms of that element. You also have a mass equal to its atomic mass measured in grams. What are you saying, Miss Hammer? This is what I'm saying. 1 mole of oxygen atoms. So if you have individual oxygen atoms and you have 6.02 times 10 to the 23rd atoms, that's going to have a mass of 15.99 grams. What? Where is that number from? Well, that number is from the periodic table. And if I pull that up, so oxygen is here. It's got a average atomic mass of that 15.999 right here. And so that's what we're talking about. So that number there is the average atomic mass. We learned how to calculate that. It also is the number of grams in 1 mole of that substance. Back here, let me make this big. back here, we've got 1 mole of oxygen, so that's 6.02 times 10 to the 23rd atoms of oxygen. It's going to be 15.99 grams because that was its number on the periodic table. 1 mole of sodium. Okay, so sodium is the element in A. If we look at it on P table, sodium, here it is. It has a decimal number of 22.990. So we're going to remember that. So sodium Na, if you have 1 mole of it, has 22.99 grams. So try this one. Grab your periodic table. 1 mole of magnesium has a mass of what? Okay. 1 mole of magnesium would have a mass of 24.30 grams, because if you find magnesium on the periodic table, here it is, has a number here of 24.305, so we can round it to 2 decimals, 24.30. Okay. So what does a mole look like, y'all? We have to remember that a mole is like a real physical thing. A mole of an element is equal to a certain number of grams of that element. So I want you to look at your periodic table, and I want you to pause this, and I want you to look at all of these elements here. I'm going to look up zinc. What you're going to notice is that on the periodic table, it's got a number of 65.4. So all of these samples here are 1 mole. Well, it's got a mass of 65.4 grams because that's zinc's number on the periodic table. Find it, here it is. Zinc, 65.38. Okay, so 1 mole of zinc has a mass of 65.4 or 65.38 grams. Okay, pause for a second and find a couple of these elements on the periodic table. And what you're going to notice is that all of these samples are a mole, and all of them have a mass equal to the decimal number on the periodic table. All right, so all of these samples are a mole. They all have a mass equal to the decimal on the periodic table. How many atoms are in each sample here? This is a big idea. What I want you to remember, all of these here are samples that are equal to 1 mole. And so all of them have 6.02 times 10 to the 23rd atoms in the sample. All right. This number here that we're talking about is called the molar mass. So when we write the atomic mass in grams, we call it the molar mass because it's the mass of 1 mole. Molar mass is the mass of 1 mole. And I like to frequently say while I'm teaching, when I say molar mass, I say molar mass from the periodic table. Okay, so I'll use that phrase a lot. Whenever we're finding the molar mass, we're going to remember that that's the number from the periodic table. It's the mass of 1 mole. So what's the molar mass of zinc? Well, here's 1 mole of zinc, and it has a mass of 65.4 grams. So 65.4 grams is the molar mass of zinc. Here's another one. It's the molar mass of sulfur. Well, sulfur is this yellow one down here. And this picture is 1 mole, and so the molar mass is 32.1 grams. Again, if we look at sulfur on the periodic table, the molar mass is 32.06 or 32.1. So the decimal number on the periodic table is the molar mass. All right, so like what's going on here? What are we trying to say? What we really want you to get is that there are 3 things that are equal to each other. 1 mole of an element equals 6.02 times 10 to the 23rd atoms of that element. That's Avogadro's number. And that also equals the molar mass in grams, and that's of that element. And all of these things are equal. And I would recommend in your notes where it says molar mass in grams, I would write yourself a little note. Molar mass is from the PET, it's from the periodic table. So that's where we find that number. All right. Here's a little bit of information that we need to finish up before we look at examples. And these are called the diatomic elements. Okay. So diatomic elements are some special elements that always exist as pairs. And we're talking about in nature. So like out there actually in the real world, these elements always exist as pairs. So you would never find hydrogen all by itself. It would always pair up with another hydrogen. Same thing with oxygen. Oxygen would always pair up with another oxygen, and it would be double. And that's why in biology you always wrote oxygen as O2. There was a reason. So the elements that form pairs and are called the diatomic elements, we do need to memorize these. So the elements are H, NOF, ClBrI. I like to call these the Hernofkelbrei elements. I'll say it again, Hernofkelbrei. If you say these elements in order, it's not a real word, but if you pronounce it that way, HNOF, ClBrI, it's Hernofkelbrei. These are the elements that always exist in pairs. What that means is that their molar mass is always going to get doubled. So later on, we're going to see an example where I'm going to do that. Come back to this if you need to, and remember that those are the diatomic elements. They always exist as pairs. All right, we're going to do a little practice before we do like real calculations. These are just some little practice problems to understand the concepts. So this right here, we should be able to just do conceptually. So if we have the element calcium and we have 1 mole of it, we're going to say how many atoms and what the mass is of it as well. The number of atoms or particles that it has, well, that's Avogadro's number, 6.02 times 10 to the 23rd. Because 1 mole of anything, whether it's calcium or argon or pencils or dogs, is going to be 6.02 times 10 to the 23rd. The mass is going to be related to the molar mass on the periodic table. So I'm going to go back and find calcium, and it's 40.078. Y'all, in general, I'm going to round to 2 digits after the decimal. So I'm going to round it up. I'm going to say 40.08. So calcium, if we have 1 mole, it's 6.02 times 10 to the 23rd atoms, and it's 40.08 grams because that's the molar mass. All right, y'all, next let's look at argon. Let's find argon on the periodic table. Over here in the noble gases. Okay, argon has a molar mass of 39.948. I'm going to kind of round that off to 40 just to kind of do some estimations. So argon has a molar mass of 40. So if I come back here and I look at argon and I know that it's molar mass, so 1 mole is 40 grams. But in this problem, I have 80 grams. That's twice as much. So that's going to be 2 moles. Awesome. So then if it's 2 moles, how many particles is that going to be? That's going to be twice Avogadro's number. So I'm going to grab my calculator here, and I'm going to do 2 times Avogadro's number. That's going to be 6.02 times 10 to the 23rd. So 1.204 E24. So 1.204 times 10 to the 24. I just doubled Avogadro's number. Why? Because I had twice the molar mass. That means I had 2 moles. All right, next let's look at chlorine. Chlorine, we've got half of a mole. Now this one's a little tricky. Half a mole means that we're going to have half the molar mass, but chlorine, big newsflash here, chlorine is one of the diatomics. So chlorine is actually Cl2. So its molar mass is doubled. I'm going to be honest, y'all. If this one's a little tricky, don't worry. It'll make more sense later when we don't do this just conceptually and we do the real math. But for now, let's talk about it. So 1 mole of chlorine would be 6.02 times 10 to the 23rd particles, but we've actually only got half of that. So we're going to do 0.5 times parentheses 6.02 times 10 to the 23rd. It's going to be 3.01 times 10 to the 23rd. And then for mass, y'all, this one's a little tricky again. For chlorine, it's Cl2. So the molar mass is the number from the periodic table, but it's doubled. So for chlorine, 35.45, but that gets doubled for the real molar mass of chlorine. So that's going to be 35.45 times 2. Okay, so 70.9 is 1 mole. But we have half a mole. So half of a mole is going to be half of that. That's going to be the 30.45 grams. Again, y'all, if that chlorine one was a little tricky, don't stress. It's going to make more sense as we move on. Next up, silver. Silver, we have 2 moles. Well, 2 moles is going to be double Avogadro's number of particles. We did the same thing with argon, y'all. It's going to be 1.204 times 10 to the 24. And then the molar mass of silver on the periodic table here is 107.87, but we've got 2 moles, so we need twice that much. So we're going to do 107.87 times 215.74. Again, that was 2 moles, so we doubled everything. All right, finally, we've got the element tungsten, which is W on the periodic table. Let's find that. Tungsten is down here. Y'all, its molar mass is 183.84. However, in this problem, we have 3 moles of it. So I'm going to take that molar mass, 183.84, times 3, 551.52. That's 3 moles. 551.32 grams. And then the mole, for the number of atoms, that's going to be 3 times Avogadro's number. 3 times 6.02 times 10 to the 23rd. Three times, parentheses, 6.02 times 10 to the 23rd. And we get 1.806. E24, 1.806 times 10 to the 24. There we go. All right. Again, if this one's a little tricky, don't stress. I'm going to show you a very clear, concrete way to always be able to solve these problems. Kind of, we did them in our head right here, but you don't always have to do that. All right. All right, so to get very exact answers on these problems, we are going to use a skill from earlier in the year. We're going to use dimensional analysis to calculate exact answers to mole problems. So in order to do this, we are going to need to always remember the conversion factors that we've learned so far. So just to kind of review those, we have learned what 1 mole is. 1 mole is 6.02 times 10 to the 23rd atoms of that element. And then 1 mole is also equal to the molar mass of that element. And we remember that the molar mass is from the periodic table. So here we go. Let's learn how to solve these problems. Number 1, what is the mass? So we are solving for grams, that's our unknown, of 7.52 moles of iron. So our goal here is to convert from 7.52 moles of iron to grams. So that's where we're starting, and that's where we're going. So just like we learned earlier in the year, we're going to put what we know over 1. So that's 7.52 moles of iron. Our abbreviations here for moles, we use MOL. And then we always include the element because it changes from problem to problem, and it's very helpful to have it included here. We're always going to include that. So iron is Fe. We're going to do times a line, just like before. And just like before, we're going to bring our unit moles of Fe down diagonal. Awesome. We remember how to do that from earlier. And then where are we going? We are going to grams. So I'm going to put grams of Fe up top. All right. Open up those ears. We are going to talk about what numbers to plug in where. So I'm trying to change my color here. All right. So up top here, I need to put the number that goes with grams. Well, the number that goes with grams is the molar mass of that element. And I cannot stress that enough. The number that goes with grams is the molar mass of that element. So to find the molar mass of the element, we'll go to the periodic table. So I have P table pulled up. We're going to go to iron right here. All right, y'all. So the molar mass is 55.845. I recommend that we are going to round these to 2 digits after the decimal. So we're going to do 55.85. All right. So in front of grams, you're going to put 55.85. Love it. Okay. Next up, what number do we put in front of moles? So the number that we put in front of mole, I'll pretend I didn't cross that out. The number that we put in front of moles, if I go back to my highlighter, moles, we put 1. Y'all, what number do we put in front of moles? We put a 1. All right, so I'm going to put a 1 in front of moles. All right, what we're going to do now is we are going to go and cross out the units that canceled. We arranged it so that moles of Fe cancels, moles of Fe cancels. Our answer worked out to be grams of Fe because that's the unit left over. And now we're ready to do our math. So remember that we multiply the numbers across the top and divide by the numbers on the bottom. So this is going to be 7.52 times 55.85 divided by the numbers on the bottom, which is 1. So let's go to our calculator and do this calculation. 7.52 times 55.85, and you don't have to divide by 1. And so our answer is 419.992. We will talk about sig figs, but for now I'm going to write down the whole thing. 419.992. 419.992. Okay, let's remember from earlier in the year, the number of sig figs in the starting position of a problem like this, which is 3 sig figs. That's how many we want in our answer. So the number 419, if we keep 3 sig figs, we're going to be rounding to the ones place right there. So this will round to 420, and we want to keep that 0 significant, so I'm going to put a decimal place there. So if I write 420 like that, it's got 3 sig figs. Awesome. Let's do the next one. Number 2. What is the mass in grams of 3.011 times 10 to the 23rd atoms of iron? All right. So we're going to start by putting what we know over 1. 3.011 times 10 to the 23rd. For atoms, I have just abbreviated it with AT, and iron is Fe. We're going to multiply by a line. So we bring our unit down diagonal. So that's atoms of Fe. And we're solving for mass in grams. So we're going to solve for grams of Fe. All right. Super important here. We are going to talk about what numbers do we put in front of the units. Well, grams, the number that we put in front of it is the molar mass from the periodic table. Grams gets the molar mass from the periodic table. So for iron in the last problem, we saw that that was 55.85. Awesome. Next up on the bottom, we have atoms. And so what number do we put in front of atoms? Well, looking at our conversion factor, the number that we put in front of atoms is 6.02 times 10 to the 23rd, called Avogadro's number. So we're going to plug that in down here, 6.02 times 10 to the 23rd. Okay, we are going to cancel the units that cancel to make sure that we set this up properly. I'm going to use blue. Atoms of iron atoms of iron. Good. The unit left over is grams of iron. All right. So we are going to calculate this number. We're going to multiply the numbers across the top and divide by the bottom. I will remind you that numbers in scientific notation in a graphing calculator or a scientific calculator need to be put in parentheses, or you're not always going to get the right answer. So in this case, what we're going to type in our calculator is 3.011 E23 times 55.85, and then divided by parentheses 6.02 E23. So we multiply the top and divide by the bottom. So let's go to our calculator and see what we get. So parentheses 3.011 times 10 to the 23rd. Remember, we do E23 in our calculator, times 55.85 divided by parentheses 6.02. Remember, to get to E, you do second, comma, just like I did there, and then 23 close parentheses. Awesome. So our answer is 27.934 ... So I'm going to write down 27.934. Let's analyze the sig figs. So how many sig figs did we start with? We started with 4, so we want to end with 4. So 2, 7, 9, 3. We're going to stop there. So we're rounding to the 100th place. And the 4 does not cause the 3 to round up, so it stays the same. So our answer is 27.93. Beautiful. All right, for this one, we've got what is the number of moles in 4.50 times 10 to the negative 20 grams of oxygen. So moles is our unknown. 4.50 times 10 to the negative 20 is what we know. So we're going to put what we know over 1. 4.50 times 10 to the negative 20 grams of oxygen. Now, this one's a little tricky because oxygen is one of those special diatomic elements that we talked about. So oxygen, every time we calculate with it, is O2. So we're going to write the chemical formula for it as O2 every time. From there, we're going to just continue calculating. So we're going to multiply by a line. We're going to bring grams of O2 down diagonal as always. And then we are calculating moles. So we're going to put moles of O2 up top. All right, let's think about this. What number do we put in front of moles? Well, every time we put 1 in front of moles. So we're going to put a 1 there on top. And then what do we put in front of grams? Well, we're going to highlight it just to help you see where this is coming from. When you have grams, the number that goes in front of it is the molar mass from the periodic table. So the molar mass is always going to be the number from the periodic table. For oxygen, we're going to look it up, and because it's diatomic, we're going to double it. So on P table, we'll find oxygen. Now its molar mass is 15.999. We're going to round that to 16.00. So doubling that for oxygen, we get 32. Very good. And again, that's the 16 molar mass times 2. We get 32. And you would do that for any of the special diatomics that we talked about. Remember that that's Hydrogen, hydrogen, nitrogen, oxygen, chlorine, bromine, iodine. You would always double their molar masses. So for this one, let's move over to our calculator. And we're going to remember to put that scientific notation number in parentheses. So 4.50, second comma gives us the E, which means times 10 to the negative 20, close parentheses, times 1, and then divided by 32. All right. So we have 1.40625 times 10 to the negative 21. We're not going to want all those digits, but we'll write them out just so that we can think through how to round it. So looking back, we had 3 sig figs to start with. In our 4.50, we had 3 sig figs. We're going to mark that. So we want 3 sig figs in the end. So 1.40, we're going to stop there at what's called the hundredths place. The 6 is going to round up the number that came in front of it. So it will be 1.41 times 10 to the negative 21 moles of O2. Excellent. All right, next up, number 4. What is the number of moles, that's what we're looking for, in 3.8 times 10 to the 23rd atoms of magnesium? So we'll put what we know over 1, 3.8 times 10 to the 23rd atoms of magnesium, which is Mg. We will multiply by a line to set up. Atoms of magnesium comes down diagonal, and what we want goes on top. That is moles of magnesium. Very good. Okay. So now we're going to think through what numbers do we put where. Moles of magnesium is going to get a 1 in front of it because moles in a conversion factor always gets a 1. Our bottom has atoms of magnesium. So we're going to color code this so you can see where the numbers are coming from. Atoms of magnesium. Atoms always gets 6.02 times 10 to the 23rd in front of it in a conversion factor. As long as it's not what you started with, you're going to use Avogadro's number, 6.02 times 10 to the 23rd. Atoms of magnesium cancels because we set it up that way, and we're ready to calculate. We're going to do 3.8 times 10 to the 23rd in parentheses. There we go. And then we're going to multiply by 1, and then we're going to divide by, open parentheses, 6.02 E23. Make sure that you're able to follow along with your actual calculator. You want to be able to do these calculations on your own. Pause the video if you need to. All right, so we get 0.63122. If we think about sig figs now, we see that we started with 2 sig figs. 0.6312 moles of magnesium is too many sig figs. So we're going to mark it just so you can see it. We started with 2. We want to end with 2. The 0 doesn't count, so we're going to get the 6 and the 3 and then stop the number. That 3 is what we're going to keep. And so 0.63 moles of magnesium is our answer. Perfect. Let's try a couple more to make sure we're real good on this. Number 5, how many atoms are in? So atoms is our unknown. How many atoms are in 8.43 moles of nickel? Moles of nickel is what we know. So we're going to put our 8.43 moles of nickel above 1 times a line. We're going to bring moles of nickel down, and we're going to put atoms of nickel up top. Very good. So then let's think through where these numbers come from. The numbers that we're going to put in. So atoms, what do we always put in front of atoms? It is always Avogadro's number, 6.02 times 10 to the 23rd. 6.02 times 10 to the 23rd, Avogadro's number. And then on the bottom, let's get a different highlighter color. Well, blue on blue is not going to work. So let's get a different color. Yellow. Okay, moles. Where does the number come from for moles? Well, it's right up there. 1 mole is always the number that we use. So we put a 1 right there. Excellent. So we're going to grab our calculator. Moles of nickel cancels. Atoms of nickel is left over. And here's what we're going to calculate. It's going to be 8.43 times, open parentheses, 6.02 times 10 to the 23rd, close parentheses, divided by 1 if you want to. All right, let's think through sig figs now. So we started with 3 sig figs and we want 3 sig figs. So that's going to be 5.07. And then we have to remember to keep the E24. So 5.07 times 10 to the 24 is the answer with the right number of sig figs. Awesome. All right, let's try one more. If you feel good on this one, you're doing great. How many atoms are in 1.0 times 10 to the negative 10 grams of gold? It's a very small number of grams, but don't worry. We're just going to solve the problem like we always do. So we're going to put our 1.00 times 10 to the negative 10 grams of AU for gold times a line, grams of AU on the bottom, and atoms of AU up top. Okay, we're not going to highlight this time, but we'll still circle and point at what we're getting. The number in front of atoms is always going to be 6.02 times 10 to the 23rd. So we're going to put that up top because it's in front of atoms. On the bottom, it's grams. And so what do we put in front of grams? Oh, this one I am going to highlight just to make sure we see it. The molar mass is the number that we put in front of grams, and the molar mass comes from the periodic table. So we're going to go back and grab that molar mass for the element AU gold. So it's 196.97. All right, and so grams of AU cancels. Atoms of gold is what remains, and we're ready for our last calculation. Okay, we're going to open parentheses, 1.00 times 10 to the negative 10, close parentheses, times, open parentheses, 6.02 times 10 to the 23rd, close parentheses, and then divided by 196.97, the molar mass of gold. Awesome. Our answer, let's think through it. We want to have 3 sig figs. And so we have 3.0, it's going to round up to 3.06. And then it has E11, so that's going to be 3.06 times 10 to the 11. And that's atoms of gold. Very good. If you didn't quite catch that rounding, the original number in the calculator was again 3.056. We're going to round to the hundredths place, so the 6 causes it to round up. So 3.06 times 10 to the 11th is our answer. Thank you so much for watching. I hope this was helpful, especially if you were absent. This is a really critical skill. So if you need some additional help on it, please come see us in tutoring. We are happy to help. Thanks for watching.